Unfortunately, we will be building on those lectures, but I'll try to provide a bit of a review in the beginning, so that you're not 100% lost. Furthermore, I want to run 2 votes by the class before starting. I always do these things by vote. The first one is regarding quizzes. I want to know if you guys want another quiz or if you're happy with the quizzes you have so far. If you did have another quiz, I promise to put maximum 1 actual question in it, the rest of them so, we're happy as we are. Yes. You want another quiz? Okay, you know what I'll do? I'll provide another quiz, but your top 2 quizzes will be your quiz mark. But I will include a 10-mark question out of 100 marks in the exam that asks you to summarize what you did for your assignment. What does that mean? Write something in advance and copy it out. That's a way of for me making your assignments countable. Right? So you should have something nice prepared that you copy out in this question. Okay? The exam will be out of 60. The assignment will be out of 20. The oral test and the class test, I'll tell you how I work that out in a second. The quizzes, counting out of 6 because somebody feels that 5 is little. Now, how the oral test and the class test are going to count is, whichever one you get the best mark for will count to 12. And whichever one you get the worst mark for will count to 2. 3. No. That's how you'll observe your mechanics marking. If you wanted your assignments, you do your quizzes, and you don't do that one at the exam, you will pass the course. Because the assignment, the text is going to mark in the exam.
Sorry, 2 quizzes. We can't quiz 1.
One, because then I reopened it and they're allowed to pull an infinite amount of time and a number of rules. So what I will do is I will design a quiz which will have a reasonable level. I'm not going to make it extremely difficult. I'll make it similar to the others. And then if you aren't happy with your current 2 quizzes, then we'll do another one. Right. If for some reason one of the marks here is missing, the other one will just come forward. Okay. So if you're happy with your test, you don't need to attend it. Oh, there was another thing I want to vote on. People have told me I'm really hot. Today, unfortunately, I have fever. And fever too. doodle, so we're going to have to find out. On Monday and Wednesday, we did the calculus of variations. I'm going to provide you a review, which is quite comprehensive in order to get us back on track. The calculus of variations essentially involves the study of maxima and minima of functions. And in fact, even today. It involves determining the stationary points of a functional. Now, can anybody tell me, does anybody remember what a functional is? Yes. A functional is something that maps a function to a real number. So a functional is something that maps a space of functions to a real number. Essentially, it's an infinite dimensional function. A one-dimensional function has one variable, x. A two-dimensional function has two variables, x and y. An n-dimensional function has n variables, x1, x2, all the way to xn. A functional has an infinite number of variables because a function has a value at an infinite number of points on the plane. Right? There's an x here, there's an x here, and all these points give the function. So a functional, which is something that maps these functions to the real numbers, is an infinite dimensional function. It's a function whose domain is a function space, so to speak, or a space of sine x, cos x, things like that. Often you can write Fourier series approximations to them, so on and so forth. Now, calculus of variations is essentially therefore the study of infinite dimensional optimization. In particular, we were interested, and when you're interested in other kinds of optimization problems, then it branches out and becomes what's called optimal control. But we were interested in minimizing, maximizing, or whatever. I'm going to write min, but just bear in mind that this is just finding station points R, which is very similar to finding, when you say grad equals to 0 in multivariable problems, finding the stationary points. So I want to minimize, maximize an integral of some functional, which I'm going to call out, for reasons that those of you on Monday and Wednesday know, of t qi dot dt from t1 to t1. Right. So what is this thing? It's an integral. An integral always returns a number, right? When it's real value inside, it will return a real number, and that in this case is the case. So what we're getting here is a single number as a result of integrating over this function. Now, when your functional is prescribed in some way, you're solving a particular problem. And the problems we solved on Wednesday, we solved the problem of, given 2 points in the plane, one here and one here, say, what's the shortest path between them? So there's a whole infinite number of class, infinite dimensional set of paths going between A and B. And the shortest one between them, as we well know, is the straight line. The straight line is the shortest path between 2 points in Euclidean space. We proved this on Wednesday by constructing. We said we have to minimize, in this case, from 0 to 1, something that looks like this. The square root of x dot squared plus y dot squared dt. And this just comes from your distance ds, your path length. So we're finding the length of a path. And then we said, well, this is pretty easy. There's nothing really special about it. So, oh, by the way, when we solved it, we had to use a methodology. And essentially the thing that minimizes this, the condition for this to be a minimum, just like the condition that grad equals 0 in multivariable calculus, is something very similar to grad. Now, I'll briefly just describe what we did, but I'll do it very briefly and I'll use a slightly different terminology that's aimed at today's lecture. So, what we did was we said, let's start with some path. When we're at a local minimum, the derivative in any direction from that path should be 0. That's how it works in multivariable calculus and in single variable calculus. When we're trying to find the local minimum of this path here as a function of x, we say d by dx should be 0 at that point. When we're trying to find the local minimum of some function, then at that minimum point we say if we go in either of these directions, d by dx should be 0 and d by dy should be 0. Now in an infinite dimensional space, a direction, an x or a y, can be any arbitrary function displacing from our current position. So what we do is we add an arbitrary function to this one. Right. So as you can see, we've varied slightly from our original path. And all that this is the function, what is the function at A and B that we've added to our curve? It's 0 there because we're coinciding here and we're coinciding here. And the displacement is elsewhere non-zero. So we say, let's take our function f of x, y, or whatever, and let's add some infinitesimal piece, some alpha times by h of x, y. When in particular, h of ax and ay is 0, and h of bx and by is 0. Now, I'm going to write this in a slightly different way. There will be a formal derivation of these things in your course notes, but I'm going to just derive it in a kind of heuristic way, which should make a lot of sense to you guys. And those of you who have been here on Monday and Wednesday will appreciate this as a heuristic way of getting at what we got. I'm going to say this is the same as just writing f of x, y plus delta f. Some small displacement. Right. And now what we like to work out is the derivative with respect to alpha of this thing. And what should it be at the optimum? If f was the optimum, what should the derivative with respect to alpha be? It should be 0. Just like d by dx and d by dy was 0, d by d alpha of any direction, where direction here is a function, added to my original function should be 0. So my condition now is d by d alpha at the extreme point must be 0. And I want to work out d by d alpha of my function upstairs, integral t1 to t2 of L of t to I and q. Right. So far this is complex. There's no physics involved. And when I take that d by d alpha in, we did this in class. I call this thing, which we didn't do, but I'm going to call this thing delta A, where where that integral is called A. We want to minimize A. So I'm going to call that, when I say delta, I read the variations. So this is the variation in f, some other function that I've added to it, the 0 at the endpoint. And that's the variation in A, when I d by the alpha of the variation in f. This is all very arbitrary, but I just want to get to this expression over here. When we work this out, we came to this answer. The variation in A is equal to the integral from t1 to t2. And the fact that we came to this answer means that you can use the result I'm going to write now as a theorem. Yes? Yes, I did. I suppose that's worth right. Now, when we bring the d by d alpha in, what we got on Monday was we got del L by del Qi delta Qi, and in fact you get a sum. Now it says lots of i's, you get a sum. Plus del L by del Qi dot delta Qi dot. And this should look like a chain rule, which is what it essentially is. Right? Because this d by d alpha, it turns out that you use the chain rule. But writing it in this notation, it looks like a chain rule with these little variation things. These variation things behave like differentials. So essentially, when we can write this out, what we want to do is we want to make everything in terms of delta Qi, not delta Qi dot. And this is because of a theorem that we proved on Monday called the fundamental theorem of the calculus of variations, the fundamental lemma of the calculus of variations. If we can times everything inside an integral by a function and equate it to 0, because we want this to be 0 and an optimum, then we could just make the thing inside 0. So what we did was we integrated by parts. And when we integrated by parts, we got, admittedly we didn't have the sum behind, but that was because we only had one variable. Integral t1 to t2 of del L by del Qi delta Qi minus d by dt del L by del Qi dot delta Qi. And what we had is plus another, plus the other terms, right? Because what we've done here is we said this is a dB, and now it's a dB, and now it's dA. Second time. It's not going to help you to get your points. Alright. So that's true. We're working T's here, right? And you already see how this is integration by parts. We differentiate this one and integrate this one to get there. And of course, we must plus our terms at the boundary, which look like del L by del Qi dot times by delta Qi between t1 and t2. But delta Qi, our variation, which is actually this thing, right? What does that look like at the boundaries, at A and at B? It's 0. So because it's 0 at the endpoints, we can say this term here is 0. And what we get out is this. The sum over I, integral from t1 to t2, del L by del Qi minus d by dt, del L by del Qi dot, delta Qi is equal to 0. And now by the fundamental lemma of the calculus of variations, we can say if the integral is 0, now the sum here causes issues. The reason why the sum doesn't match is because these delta Qi's are independent, as we've shown previously in other situations. and as is true in this case, by definition. But ignoring the sum, the fundamental lemma of the constant variation says that if this integral is 0, then the thing inside is 0. And so indeed we have the result del L by del Qi dot minus d by dt del L by del Qi. Whoa, there's no dot here. Dot here. 0. And these were very familiar looking equations. And on Monday it was quite a revelation because we were doing it in a more interesting way than this. And we asked a lot of questions about complex variations, and we went through this derivation, and bam, out came equations that we really were familiar with. The Euler-Lagrange equation. And the reason why they're Euler-Lagrange equations is Euler derived them before Lagrange, working on variational problems that had nothing to do with mechanics. Problems like finding the shortest line between A and B. Problems like minimizing energy over some finding paths that minimize. Alright, so now we have this equation in a completely new context. We have it as a first order necessary condition for optimality in the context of the calculus of variations. And it's got nothing to do with mechanics. In this particular instance. Now, what we then discovered was that in fact, you could use this equation to solve variational problems. And we solved the minimum distance between two points problem by minimizing the integral of x dot squared plus y dot squared dt between 0 and 1, where x of 0 is equal to ax y of 0 is equal to dx x of 1 is equal to ay plus b ay dx dy. We solved this problem and we got the result that alpha x plus beta y must be equal to gamma, which is the equation, of course, for a straight line. So we got that the answer is, of course, that these guys are straight lines. Yeah.
Sorry, I'm lost now. I forgot what you said. Can you go back to that argument of h of xy?
Yeah?
Yeah, alpha x, h of xy.
Yeah.
What did you say about that?
So I said that when we did this on Monday and Wednesday, alpha h of xy, which is some small parameter alpha, multiplied by a variation function h. And it should have held for all possible variation functions. Now I said over here that we could just call alpha times h delta x, my variation. That's it. I'm just finding a new name for it. And then everything else follows like what we did earlier. Only now I'm writing delta A for that d-by-d alpha thing. That thing that we said must be 0 for all h.
So h of xy is
h of xy is a small variation. So exactly, if I take my initial path and I add a small variation to it, that small variation, this thing that I'm adding to it, this is my h of xy. Well, and then if I add different multiples of it to f, I get different things. I get a whole family of different paths. And they are parameterized by alpha, correct? And when I take d-by-d alpha, I get a result. Alright, these will all be in the middle. Chapter 4, the final chapter. Now, we have here our results that we apply to this to get straight lines. And then we solve the more interesting problem, because everybody knows the shortest distance between 2 points on a plane is a straight line. But not everybody knows what the shortest distance between 2 points on a sphere is. Certainly there's a lot of different things that look straight on a sphere connecting 2 points, but which ones provide the shortest distance? And we solved that. It looked like integrating from 0 to 1 r times square root of beta dot squared plus phi dot squared sine squared beta dt for theta defined at the boundaries, similar way to x and y there. And by performing some clever rotations and by considering things that we could define as cyclic coordinates, we were able to solve this problem. And our answer was that the geodesics, the shortest paths between 2 points on a sphere, were the great circles, essentially, the diameters of, not diameters, the circumferences, I suppose you'd call them, of the sphere. These great circles that have the same radius as the sphere going around the sphere. There's always a unique one connecting any 2 points on the sphere, and we showed, quite generally, that between any 2 points on the sphere, the shortest path is that section of this great circle going those 2 points. Right, and that's essentially where we left it. And then at the end of Wednesday, I said, now we solved some variational problems using this equation. We solved for straight lines, we solved for the shortest path on a sphere, and in the oral test today, people are solving for the shortest path on a surface that they were given between 2 points. Now, we've done this kind of thing, and it's completely different. It's not mechanics. It's shortest path, it's minimization, it's optimization. But there must be a link, because we're using the exact same equations. These are the equations that popped out when we performed calculus of variations, but these are also the equations that popped out when we looked at Lagrange's approach to mechanics, going through the Island-Bayes principle, the principle of virtual work, and so on and so forth. The question is there some relationship between the two? And there has to be. And this relationship is, or finally called it, the deepest result in mechanics, the deepest result in physics, in fact. It's a very profound story, which basically says that nature is an optimization engine. It says the following. It says, okay, if I'm minimizing that, then I must solve these equations. But likewise, if I solve these equations, I must be minimizing a function. This function, which we call the action, the integral of the Lagrangian dt. So, what it says is that if I take the state of the universe now, and I take the state of the universe in 10 seconds time, and I observe every particle, how it's moved during those 10 seconds, where it started and where it ends. And that's all the information that I know. It's like a boundary value problem. Normally we phrase problems in mechanics as initial value problems, but now I'm phrasing it as a boundary value problem. I know where we start, and I know where we end. And it says that of all possible paths that all these particles could follow in between those two times, nature chooses the path that minimizes this integral. That's a very interesting result. If I start this chalk here, I end it on the floor. In between, the motion that it traveled in order to end up where it ended up, and in order to start where it started, was precisely that path that minimized this integral. Out of all the possible paths it could have traveled, all the infinitely many different